A year ago, I came into discussion with Adam and other guys about quaternions. Should we use them? Should we introduce them into APL? And, well, I know quaternions since decades for mathematics, and I know from that time that they are used somewhere in solid mechanics, and I learned that they are used in image recognition and gaming. So I thought I really would like to know how it is really done. So I started reading a bit, and my talk is about to tell you how they use it and what you can do with quaternions, and how easy, obviously, how easy it is to use them in APL. So you know all about the real numbers. Real numbers are a field. You can do a lot there. Everywhere where you cut the real line, there is a number. So there are really many numbers there. But there's one problem: you can't solve the equation x squared plus 1 equals to 0 in real numbers. So you need to have more numbers, and you come out with the complex numbers. Complex numbers are very nice from the algebraic sense of view, because you can, every equation, every polynomial has a root in C. Okay, so if you think of real numbers, complex numbers, how does it go on? Is there any field above there? And, well, definitely there are fields above there, but they are far, far away from C. Dimension is infinity. So the real question is, are there finitely dimensional fields above there? And this can't be the case, because if you have an element not in C, you take its powers, and because it's only finite dimension above it, some powers must be linear independent, and this gives you a polynomial above C whose roots are in C. So obviously there can't be anything, any field above there. But there are algebraic objects with less control. So a field, you want to have the multiplication to be commutative. If you multiply 3 by 3 and 4, or 4 and 3, you get the same result. So if you give up this idea to have commutative multiplication, there is more, but only one field. It's a single field there. The only finite dimensional skew, you call it skew field or division ring. And the only finite dimensional skew field above C are the Hamiltonians or quaternions, nothing else. So it's a single, really a single object you have there, and you can't find anything more there. So we have the skew field of Hamiltonians, and it's called, it's due to Hamilton, who is an Irish mathematician and physicist, and he lived in more or less in the first part of the 19th century. So I'm telling you only about old stuff, but new applications. Okay, here we are. So I'm back to my slides and try to find the correct one. So we did that. This is the proof that you can't have a finite field above C. And the theorem of Gelfand-Mazur tells you that every finite dimensional skew field above R is ELR, C, or the Hamiltonians. And now we come to the definition of the quaternions in the same way as you may define complex numbers as the real 2x2 matrices of rotations and stretching. We will define the Hamiltonians as 2x2 matrices above C. Now all the complex 2x2 matrices is a bit much, and they have terrible things like elements killing itself, which you do not want to have in a skew field. If you check these two matrices and calculate the product, you get the zero matrix. You do not want to have things like this in a field or in a skew field. So you go a bit smaller. You only take several of these, and you take the identity matrix, the matrix with I, the complex unity, and minus I, minus 1 and 1, and I and the non-diagonal. These four matrices are really, really connected to the spin matrices, to the Pauli spin matrices, which are used in quantum mechanics. Okay, and the set of all Hamiltonians is just a linear combination of these four, and you can write them as a matrix with V complex conjugation of V and W and minus W complex conjugated. So this is the set which we want to be all the Hamiltonians. So we have immediately, because we are working inside the matrices, that we can add them, that we can multiply them, but we must be sure that we get the same type of matrices. Otherwise, it's not a closed set. And this is just done for the multiplication, by multiplying everything out and checking. And what you realize that this part is the same, should be the same as this part, and this part is the same, but this the sign of this part, and so on. So you can compare it, and you realize, yes, the product of two Hamiltonians is again a Hamiltonian, so you have a nice set. The second, what you realize is if you take H1, H2, and H3 and take the square of it, you get minus H0. And this is really compared to the complex numbers. If you take the square of I, you get minus 1. And this is the 1 because it's the identity matrix. So in a way, H contains 3 times the complex numbers. Okay. And the next thing, which is really nice, and this really goes close to rotation. If you multiply H1 by H2, you get H3, and so on. And if you do it the other way around, you get minus 3. And this is really comparable to the cross products of vectors. The unit matrix in x direction times the unit matrix, the unit vector in y direction gives you the z direction, and so on. So really, you can compare these. And this definitely demonstrates to you that multiplication is not commutative. Okay, so in a way, we have 4 real numbers, and we map them on the Hamiltonians, and this map is really respects vector addition, matrix multiplication, and scalar multiplication. So it's a vector homomorphism, and this is really the model which we take later on. We look at the real numbers with the correct multiplication, and then we have the Hamiltonians as a 4-dimensional real space. We must think about the inverse, because a skew field, in a skew field, every element has an inverse, and you just do it in the standard matrix way. You divide by the determinant, you exchange the diagonal elements, and the non-diagonal elements gets a minus sign. Then you have the inverse. This is standard from matrices. Okay, and what I stated here as well, the center of Hamiltonians are the real numbers, and this you can check by direct calculations. So in a way, we have the base of the Hamiltonians, we have 3 copies of the complex numbers, which are here, and in the middle we have the center of the Hamiltonians, which is the real part. Okay, now I would like to concentrate more on the usual way to show the Hamiltonians. We take them as a 4-element vector, and the multiplication just comes from matrix multiplication. You calculate through it, and you get these formulas. So it's a bit complicated. You can't. It's a bit difficult to keep it in mind, but you write it down once, and that's fine. Yes. Okay. And we have the inverse, which we just took from the matrix inverse. So the next part is how to do it in APL. I didn't find an easy way to do the multiplication. You just find some idea how to write everything down. But the inverse is quite easy. You can write down d-fun and the division as well. Then this is the conjugation. I'll come back to it, and this is the symmetric difference, which you all can write down in an easy way. And well, you can start calculating it. What is the inverse of 0, 0, 1, 1? It's 0, 0, minus a half, and so on. So there's nothing. This is something of interest. So this is like a cross product of the x vector and the y vector, which gives the z vector. As in the complex numbers, you talk of complex conjugation, and the complex conjugation of a vector A, B, C, D is a real part which stays, and the others get a minus sign. Okay, now there's important things to talk about units. What is a unit? You got from matrices, you got the idea of a determinant. So if the element has determinant 1, it's a special matrix. And the same we do with the quaternions. If we define the norm, which is the determinant of the matrix, and the norm is multiplicative as the determinant is, so we can look at the unit quaternions. These are all the quaternions whose norm or whose determinant is 1. And they form a group. This means if you multiply 2 of them with each other, you again get a quaternion, a unit quaternion, a quaternion of norm 1. And if you compare this definition of the unit quaternions with the origin of the Hamiltonians coming from the matrices, you realize that it's exactly the special unitary group of 2 by 2 matrices. So again, something to compare it with in matrix theory. Okay, now in the same way as we split in the complex numbers real and imaginary part, we do it with the quaternions, but we have 3 imaginary parts. But nevertheless, we divide the Hamiltonian space in 2 parts, the real and with a direct sum of a 3-dimensional real vector space, and it's called the imaginary part. And it's quite important now to really look at these 2 different parts and see how they behave when you multiply the vectors. If you multiply A1 and the vector V1 with A2 and the vector V2, you get the product of the 2 real parts minus the scalar product of the 3-dimensional vectors. And you get the scalar multiplication of the 2 vectors plus the cross product. And this is the important thing to realize, that the cross product is there. And, well, I think it's not so surprising as I talked to you already earlier and showed you the correspondence to the cross product. And you find the inverse, which is nothing really surprising here. Now, if you think of cross products and rotations, you always think of an axis and a rotation angle, and the polar representation of unit quaternions really comes close to that. We have a real part which we say is a cosine, and it's sine times a 3-dimensional unit vector, and they build a unit quaternion. And we really want to see later on how this angle is related to the rotation this unit quaternion stands for. Now, it is standard in field theory, non-commutative field theory, that you always get nice mappings if you calculate the conjugation with an element. So we take a vector in the 3-dimensional complex area and calculate the conjugation with the units quaternion. Conjugation means you multiply with this element, and on the other side you multiply with the inverse of this element, and you see what you get out there. Now, if you calculate through it, you realize that you get 2 times alpha here and 2 times alpha here, and this is a special expression which I will explain a bit later on as far as I need it. So having calculated this formula, you immediately can write down a 3-dimensional rotational matrix, and, well, yes, it's not, I do not want to look into it any further, because it's more important really to check what this rotation makes. But before that, I really want to make sure that we really get the same results. This is the rotational matrix as described earlier, and this is the function which takes the conjugate with the two elements. And if I conjugate the the unit matrix with the vector, the complex part, and a real part, I get this four-dimensional element, a Hamiltonian. And the other way is to calculate the rotational matrix and multiply it with the three-dimensional vector. I get the same result in the last 3 dimensions. So this is really just to check and see that it's the same. Now, I state the theorem that the conjugation with the quaternion is rotational about the axis omega dash, and the angle is 2 alpha, not alpha, but 2 alpha. And this was the result I got earlier. Now to check that it is really a rotation, yes, I check what it is, what it does with the vectors, and really from this calculations, we see that it is. You get the right result. The axis is not touched at all, and the others are rotated in the same way as the x and the y parts in the plane are rotated. So you would get the same formula. We have the x comparable to the x-axis, the e dash, and comparable to the y-axis, omega cross e dash. Okay, so we have a map from unit Hamiltonians to the three-dimensional rotational matrices by defining with the Hamiltonian S the rotation given by the conjugation with this quaternion. But we have a kernel, so the kernel is rotation about 180 degrees, or taking the minus of the vector. And this really gives a map from S divided by plus minus 1, comparable to the special unitary matrices divided by plus or minus identity to the special orthogonal matrices of dimension 3. Now I'm going to image recognition, and well, I don't mention gaming, but it's in the same area where they are really important. The first thing I checked is, why are they so important? Is it really cheaper to multiply Hamiltonians with each other than to multiply matrices with a vector and so on? And the real important thing is that if you multiply 2 matrices with each other, you get 27 multiplications. If you multiply 2 unit quaternions, you only get 16 multiplications. And this makes the benefit out of it, because in general, if you compare a moving body and you want to compare it to the initial object, you have a lot of multiplications in between, and to get the final rotation, you have to multiply all these matrices or quaternions with each other. So it's each time only 16 multiplications compared to 27 multiplications. This is the real benefit you get out of it. Okay, so now I would like to give you an example of how it is used, or how you can use APL with it. Think of a model. The small example I give you are the corners of a house. And you have somewhere a house in the scenery, and you want to compare the two. Are they identical or not? So the first thing you can do, you decide 2 corners, one of the model and one of the scenery, which are the same, so you move them together. And what is left is to calculate the rotation you need. Okay, so you have to find a rotational matrix which rotates the model to the scenery. And you calculate the error you do depending on the matrix you use. Now, you have several corners of your house, and you just check for the corners, the difference in the corners, and you have the matrix here, and you replace the matrix by the Hamiltonian. So you multiply this equation by 1, and 1 is the norm of Q squared, because Q is a unit Hamiltonian. And now you can move the Q inside the first norm, 1, because of this Q to the minus 1. Yes, I multiply it once from the right, and I multiply it from the right. So it's SIQ and QMI, and this Q is goes away. Now, the most important thing, and this is to me is the key point of this calculation, the map from Q to this expression is a linear expression. It's linear in Q, so you can write it as a matrix. And the square of a vector is a vector multiplied with its transpose. So you get the transpose of the matrix inside, and it's the sum of the matrices you get here. And this sum of a matrices is a symmetric matrix, which is semi-definite at least. Mainly, in most times, it's positive definite. Okay, so you get this expression, and what you have to find is you have to find the the Q which gives you the least error, and this is the eigenvalue, the eigenvector of the smallest eigenvalue. So you are within symmetric matrices, you are discussing with symmetric matrices, so this is a well-known fact you have there. Okay, so how to calculate the eigenvalues and eigenvectors of a matrix? There is the method of Mises and of Wieland. Mises calculates the biggest one, the biggest eigenvalue. Wieland takes the inverse of the matrix, so the smallest gets the biggest, and he uses this to do it. So I just set up here the model and the scenery with some noise on it so that the error can't get 0. And I have the two buildings. This is the model, and this is a house in the scenery. And I translate it to get 2 points identical. And now I go back to the calculation. If you think of the matrix AI, these are the maps of the unit Qs. So to create the AIs, I take the unit vectors on Q for unit vectors, and I do all the multiplication. I multiply Q with the model on the left and Q with the scenery on the right, and I arrange everything, and I get the matrix B, and I use Wieland algorithm to get the result. So this is the minimal, the vector with the minimal errors which you get there. To compare Mises and Wieland's algorithm, Mises' algorithm takes a vector and multiplies it with itself until there is no change in it, and then this vector is the eigenvector to the biggest eigenvalue, and you can calculate the eigenvalue. Now, going to Wieland's algorithm is just replacing the matrix which is with its inverse. So, but you don't invert the matrix, but you solve the equation or the set of equations all the time. So this makes it easier, quicker in calculation. Okay, and then at the end you get the result, and I produce all the errors here. The biggest error is not the 1, but the biggest error here is produced by an error in APL. 0 divided by 0 is 1, which I don't like at all in APL. 0 is rank error, which I like much more. But it's always, if I get a 1 somewhere where I don't like it, it's because 0 divided by 0 is 1 in APL. Okay, so, and this is finally what I could draw out of the results. So you see that the model rotated to the scenery looks very similar to the scenery. That's the end of my talk. Here's some literature which I use to read everything and to do everything. So I really like this part of work because it's a lot of algebra which I really like. This is the origin of my university work, and it's my preferred work, my preferred part in mathematics, and combine it with APL is really, really fun. Okay, thank you very much.